Thank you. So this is joint work with Neil and with Kevin, who's here in the audience. So today I'm going to talk about iterative combinatorial auctions. So what I mean by that is auctions where bidders are not just bidding on a single item, but bidding on bundles of items. And an iterative auction where they're not just making a single bid, but they're bidding over multiple different bidding rounds as they gain information and make bids at higher and higher prices. And the most common place you see these is in spectrum auctions, where governments auction the right to use EM spectrum to, say, telecom companies so that they can operate in major cities around the country. These spectrum auctions are complex. They often have dozens of bidders bidding on bundles that have hundreds of different licenses, and bidding can go on for maybe even 100 rounds, taking weeks. And they're also very high stakes. These can take in over $1 billion of revenue, so strategic bidding is potentially very lucrative. And so the big questions that come to mind when you think about these kinds of auctions are, what should bidders do? When a bidder is faced with one of these auctions, how should they bid? And when a designer is trying to figure out how to set the rules of the auction, how can they predict whether a change to the rules will improve or hurt revenue? And so what tools could you use to think about this? Well, you could write down a model of the auction and try to find its Bayes-Nash equilibrium. That would work if we didn't need to make such restrictive assumptions to do it. This kind of analysis generally needs to make really strong assumptions like that there's one product and that everybody has perfect information about everyone else's values. You could also try to write down the extensive form representation of the game and throw it into a traditional equilibrium solver. But these things have enormous extensive form representations, and so this tends to be infeasible too. But doing something like this ahead of the auction is really necessary, because just doing field testing and learning from what worked and what didn't in the past is just throwing away a lot of money and potentially risking billions of dollars. And so the question we want to ask is, can off-the-shelf multi-agent reinforcement learning algorithms help? Can we take algorithms that were originally designed to solve games like poker, which shares a lot of similarities with auctions, and use them to understand how bidders should behave? Of course, I'm not saying that these Fortune 500 companies should use an autonomous superhuman bidder. Of course, nobody's going to risk the future of their company on this kind of bidder. But even if they don't, this sort of trained example of strong bidding behavior can be a useful way for bidders to build a strategic playbook to understand what kinds of situations they might run into in these auctions, and for a designer to evaluate the likely costs and benefits of a change to the auction rules. And so in this talk, I'm going to tell you that these sorts of algorithms are not a silver bullet, and using them effectively takes a lot of care. And you still do need to model the auction carefully. You need to navigate some pitfalls of common algorithms, and you need to be careful about how you validate and interpret the policies that you've trained. But when it's done right, this can be a powerful tool that really nicely complements the sort of pen and paper analysis that we can do. I'll show you a case study that for one potential rule change to a common type of auction in practice, the bidders make really non-trivial behavior changes, which leads to substantially different revenue and welfare. So let me start by talking about how to model an auction. Our dream when we started this project was that we could just write down all of the rules of one of these spectrum auctions in some reinforcement learning environment and throw an algorithm at it, and voila, we get an equilibrium. Unfortunately, that's just not the case. You end up, when you do that, with a game tree that is just simply too large for any learning algorithm to have any hope of making any progress. And so it's critical to control the size of the game, to limit the number of information states without losing any of the key strategic elements that make an iterative combinatorial auction what it is. And thankfully, we can do that. There are many choices that we can make that can limit the size of the game tree. We can restrict the number of actions. Instead of studying auctions that have bundles with hundreds of products, we can look at auctions that have maybe just 2 or 3 products, which still has a bit of a combinatorial flavor, but doesn't have an enormous combinatorial explosion in the action space. We can take continuous action spaces and discretize them. In these auctions, it's common to ask bidders both what bundle they would like at a certain price, which is a discrete choice, but also what price they'd be willing to pay for a certain bundle, which is a continuous choice. And multi-agent RL algorithms can usually handle one of these types of action spaces, but not both. And so finding ways to ignore or discretize continuous action spaces can help to make things tractable. It's useful to limit the auction length. I said before that these auctions can last maybe 100 rounds, but even when they do, most of the action is compressed into just a few rounds of the auction. And so keeping the model of the auction short, making the initial prices high and making prices increase quickly can maintain a lot of the same complexity without needing an enormous game tree. And finally, one caveat that we were really surprised to find was that these auctions, in theory, can have histories that have infinite length. If every bidder just says, yes, I would like to buy it no matter what the price is forever until the end of time, the auction will never end. And while no bidder will ever actually do that, a reinforcement learning algorithm sure will try it. So finding ways to restrict the algorithms from trying these actions at all, to say these are simply not actions that you may use, is really necessary. But I'll note that, well, it is necessary to restrict the size of the game tree. It's not so important exactly what happens within this restricted game tree. There doesn't need to be so much structure between the different actions. And so it's really quite easy to model asymmetric bidders with different value functions, or really case-based rules that have if-else statements that would be a mess to handle analytically. And it's no problem at all to handle imperfect information where bidders don't know each other's values. Okay, so once we've got a game, what algorithm should we use? Broadly, multi-agent RL algorithms vary along two key dimensions. The first is how they represent their policy. Some represent the policy as a lookup table, just a table for every information state of the action probabilities that they'll play in that state. These are nice. They tend to be stable. They tend to be easy to train, but they don't scale so well. Once you get to large enough games, if you can't fit the entire game tree in memory, then you can't fit the policy in memory either. At the other extreme, there's function approximation, representing the policy with a neural network. And while this does let you scale to large games, because the size of the neural network doesn't have to depend on the size of the game tree, it can be a bit trickier to train. It's a lot more finicky and takes a lot more tuning to work well. The other key dimension is what part of the game tree gets explored in every iteration. Some algorithms will just look along a single path in each training iteration. They'll maybe play a single history through the auction. They'll update their policy based on this one path. That way it's fast to perform a single training iteration, but it can struggle to train effectively. It can get stuck in it can sort of thrash around and not cover parts of the game tree that are important. On the other hand, you can consider every counterfactual action in every iteration. You can enumerate the entire game tree. This tends to work better. It tends to, when it's possible to enumerate the entire game tree, it tends to work quite well. But of course, this doesn't scale to large games where you can't enumerate the entire game tree. Some other considerations that we talk about in the paper that I'll just brush over quickly here. It's important to break in differences between actions that give identical rewards. In some of these auctions, it's possible that two actions can really just end up having the same effect. And in that case, learning algorithms tend to just mix between them randomly and thrash around, which really hurts convergence. It's also helpful to restrict policies to pure strategies, both because it makes things easier to evaluate and because it's computationally easier. And finally, with stochastic learning algorithms, it's possible to find multiple equilibria simply by running it with multiple random seeds and seeing what different equilibria pop up. Now, let me talk about what to do once you've trained a policy. First of all, it's important to know whether you found a good policy or not. And the way to do this is to compute Nashconv, which is the sum of each player's regret. If each player was allowed to best respond to their opponent's policies, how much utility would they gain? Ideally, they would gain nothing. You'd get a Nashconv of 0, and then you know that you found a Bayes-Nash equilibrium. And in relatively small games, you can just do this with brute force. You can compute the exact best response with a depth-first search, and you can compute Nashconv exactly that way. In larger games, when that's not possible, when the depth-first search doesn't scale, it's still possible to get a lower bound on Nashconv by finding a best response as a single agent RL problem, finding an approximate best response, which gives an approximate regret and a lower bound on Nashconv. Finally, I'll say, well, it would be nice to interpret exactly what these policies are doing. Interpretable ML would be broadly amazing. It can be useful even just to look at what statistics come out of these algorithms, what the revenue, what the welfare, what the auction length are, and trying to get some insight from those. But one caveat there is that if you're looking at multiple equilibria, there's no real reason that the distribution of equilibria you find from running these algorithms multiple times has any connection to the distribution of equilibria you find when people play these games multiple times. And so I think it's more meaningful to report the range of outcomes that can happen rather than the distribution or the average. Let me turn now to a case study on a specific kind of iterative combinatorial auction that's used in spectrum auctions. So these are called clock auctions. The auctioneer has a set of regions, and in each region, they have a number of identical items that they want to sell. You can think of the regions as maybe cities and the items as licenses to use some of the bandwidth. So in a basic model of a clock auction, the auctioneer starts by setting initial prices for every region. And then every round, they ask every bidder to make a bid, which is a vector of how many licenses they would like to buy, how many items they'd like to buy in every region. If they can fulfill everyone's bids, if the demand is less than or equal to the supply everywhere, then the auction ends and everybody gets what they asked for. Otherwise, the auction continues. The auctioneer reveals some information to the bidders, like the total demand in every region, and they raise the prices on the regions that were over demanded. It's clearly we need to raise the prices there so that people will have less demand. Well, this is a simple model. There are really a lot more twists in practice. Let me tell you about one. In practice, it's common to add a rule called an undersell rule. This roughly says that if you were willing to buy a lot of licenses at a low price, you're probably still willing to buy a few licenses at a higher price. And so once demand has gone above supply once, we can never let it go back below supply. So to give you a concrete example, I've got a picture here of a region with 4 licenses available. And in round T, the green bidder bid for 3 of those licenses, and the red bidder bid for 3 of those licenses too. So in total, the demand was 6, and we had to continue the auction. And then in round T+1, they both submitted bids asking to drop some of their demand. They both asked for 1 license rather than 3. And according to the undersell rule, we can't fulfill these bids. That would give us demand less than supply. So we can do one of 3 things. We can either fulfill one of the bidder's bids completely. So on the left, we could let the red bidder let their drop go through and leave the green bidder holding a demand of 3. Or we could do the opposite. We could let the green bidder's drop go through and leave the red bidder holding 3. Or we could partially process both of their bids and leave them both holding 2. So how we choose between these is a decision. So 2 natural ways to do this. The first is to something that we'll call the drop by bidder mechanism. So we'll pick a random order over the bidders, and one at a time, we'll process their bid as completely as we can without violating this undersell rule. So under that model, half of the time we would get the first outcome, half of the time we get the third outcome, and we would never get the middle outcome. An alternative is we could think of a drop by license rule, where instead we would randomly order the 4 individual units of drop requests. And we would process those one at a time until the undersell rule stops us. And then we would get half of the time, we would process 1 drop request from both of the bidders. And the remainder of the time, we would process one of the bidders completely. And so this is a bit of a subtle rule change. It's not immediately clear what this should do to the revenue or the welfare of an auction, because it could really have a non-obvious effect on what bidders do. So we experimented with a small auction. We looked at an auction having 2 bidders bidding on 2 regions with 4 licenses in the first region and 1 license in the second region. So with 4 licenses in the first region, you can sort of see this behavior of coming up against the undersell rule that I showed on the previous slide. The bidders had their value functions drawn from the MRVM model, which is a pretty realistic model of bidders' values in spectrum auctions. And for different instantiations of this model, we came up with 5 games, which had 500 to 700 information states. And so we ran 2 popular multi-agent RL algorithms on these auctions. The first is a Monte Carlo sampling variant of counterfactual regret minimization. And so under the dimensions I was telling you about earlier, this stores the policies in a tabular format. And in each iteration, it explores many counterfactual actions. It looks at a large chunk of the game tree. We found this worked pretty much off the shelf. It was really easy to use. It found policies with a Nash conv of 0 or a very low Nash conv, and it didn't take much tuning at all to make it work well. Second, we tried at the other extreme, an algorithm called proximal policy optimization. So this is a function approximation method. The policy is a deep neural network, and each iteration, it only looks at a trajectory on path. We found that we could make this work, but it took a lot more tuning. With the right hyperparameter settings, we could, again, get policies with a Nash conv close to 0 or equal to 0. But finding those hyperparameter settings took a pretty extensive search. And so what we found was that there is indeed quite a significant difference between these two tie-breaking rules. So on the left plot, in blue, I'm showing how often bidders run into these tie-breaking scenarios under the drop by bidder rule set. And what you can see across these 5 different games, across many of the different equilibria that we found, they tend to run into these tie-breaking scenarios about 1 in 3 or 1 in 4 auctions. On the other hand, in the drop by license rule, they never run into them at all. Bidders learn that triggering these tie-breaking scenarios is really damaging to their utility, and so they learn to completely avoid it. And so the way that they do that is they learn to coordinate in a way, alternating their drop requests so they never both ask to drop demand at the same time. And you can see what this does to the other metrics. It tends to make auctions that last longer. It tends to increase revenue because longer auctions have more price increments. And it also tends to decrease welfare because bidders are less able to express what they really want. And so this is an example of a small, pretty subtle but complex change to the auction rules, producing a non-obvious change in behavior that really makes meaningful differences in auction outcomes. So let me close just by saying, I hope I've shown you that I think multi-agent reinforcement learning is potentially a very powerful tool for economic analysis, especially for auctions. While it takes some care to use it well, it's no silver bullet. It really can complement the existing methods that we have and can tackle problems that are at a scale that traditional methods just can't handle. Thank you. Yes.
So, did you actually compute the Nash conv exactly, or when you said that you were close to equilibrium or exact equilibrium, or were those based on the lower boundary with RN?
Yes, so those are, in these experiments that I showed, we were looking at small enough games where we could compute exact Nash conv. In the paper, we also look at games that are about 50 times larger, and there it became a lot trickier. We couldn't finish computing Nash conv in an hour. So I think for even larger games, we would have to use some sort of approximation. But these are, we know that these are exact Nash equilibria.
Okay, and I guess kind of a side point, I wouldn't really call these multi-agent RL algorithms, especially MCCFR. That's pretty much computational game theory and not RL, but that's something.
Yeah, I've heard different takes from different people. I think that people who do reinforcement learning, like a lot of people would call this more of like a search algorithm in a way. Yeah. Yeah.
You said earlier in the talk that you restricted yourself to pure strategies. I don't really know what you mean by this, especially if you're using something like MCCFR, which inherently doesn't use pure strategy. So what do you mean by that?
Yes, good question. What we mean is that we train a mixed strategy. And at the end, we found that generally these mixed strategies were putting most of the probability on a single action and very low probabilities on the other actions. And so we sort of round these distributions. We say round up the highest probability to 1 and round down the lower probabilities to 0. This is especially useful for PPO, which has a reward for having entropy in the policy. So there's always some entropy in the probability. So having a way to remove that entropy for evaluation is useful.
And I guess you would be doing this for MCCFR to the aggregator.
That's right. Yeah.